We have seen in the previous lecture that radiation is a different form of energy transport than conduction or convection. In many practical situations, conduction, convection and radiation occur simultaneously. For example, the heating of a kettle of water involves conduction, convection and radiation. This means that the total energy loss consists of all these contributions. However, the contribution of each term could be quite different. The question is, when does radiation play a role? In-house you find many examples. If you are cooking, convection and radiation play a role. And in case of your central heating, a similar combination of heat transport is important. We have seen in the previous lecture that a black body is an object that absorbs all the incoming radiation and that the heat flow as a result of radiation can be described by Stefan Boltzmann's law. To illustrate the contribution of black body radiation, we take two parallel plates with equal surfaces. The net radiation phi black can be obtained by looking at both surfaces. So the radiation from 1 to 2 is equal to phi black 1, 2. And from plate 2 to 1 equals phi black 2, 1. The net radiation between the two plates is now equal to the difference of these two contributions of phi black net. We see that if the surface area and temperatures of the plates are known, we are able to calculate the net heat flow between the two plates. However, black bodies do not really exist. A first step to real bodies are the so-called gray bodies. So if we consider two gray parallel plate surfaces instead of black surfaces, only a part of the incoming radiation from each plate is reflected by the other plate and vice versa. So if we now write down the heat flows of both surfaces, we obtain phi gray 1, 2 and phi gray 2, 1. If we now eliminate phi gray 1, 2 and phi gray 2, 1 and apply Kirchhoff's law, which states that in an equilibrium the emission and absorption coefficients are the same, we obtain the following expression for the net flow by radiation between the two gray surfaces. You can see that if the emission coefficient approaches the value of 1, we obtain the expression for black body radiation. In practice, the surfaces are not always nice flat plates, but have different forms. Depending on the geometry of the surfaces, the expression is different. So quite often the net heat flow is expressed in terms of an effective emission coefficient, which depends on the emission coefficient of both surfaces. In practice, it is common to write the heat flow through radiation in a similar way as by convection. That means in terms of a heat transfer coefficient and a driving force delta T. If you combine both equations and assume that the surface area of both objects is equal, you can obtain the heat transfer coefficient. This expression is often approximated by this equation. In the derivation of this expression, use is made of the following approximation and the introduction of the average temperature T between the two surfaces. Realize that this heat transfer coefficient, H, radiation, does not only depend on the constant sigma, but also on both temperatures and the properties and form of the involved surfaces. You can check that the error made by this approximation increases as the difference between T1 and T2 increases. To illustrate the effect of radiation, we take a thermometer which hangs in the middle of a room. The temperature of the air in the room is equal to T air, and the temperature of the wall of the room is T wall. The wall temperature is lower than the one of the thermometer. What temperature does the thermometer show? We expect that the thermometer indicates the temperature of the air. The problem here is that the thermometer sees the colder walls. This means that heat is radiated from the thermometer to the wall. As a result, the thermometer loses energy and the temperature will be lower than the temperature of the air. On the other side, as a result of the temperature difference between the air and the thermometer, heat will be transferred from the air to the thermometer by convection. In a steady state situation, an equilibrium will occur between the heat by radiation and the heat supplied through convection. Substituting the heat transfer coefficient for radiation gives us an expression for the temperature difference between the air and the thermometer. To illustrate the effect of radiation, we take an average temperature of 300 Kelvin, a temperature difference between thermometer and wall of 10 Kelvin, an emission coefficient of 0.05 for the thermometer and a volume of 6 watts per square meter per Kelvin for the heat transfer coefficient. If we substitute all these values, we see that the temperature difference between the air and the thermometer is about 0.5 Kelvin. This example shows that even at room temperature, the effect of radiation could play a role. In many situations, radiation occurs simultaneously with free convection. Examples are radiators in houses where free convection and radiation are combined. If we calculate the heat loss by free convection of a radiator, we see that the heat transfer coefficient for radiation and free convection are of the same magnitude. We will illustrate this in one of our glass plate examples. Realize that many radiators are also constructed for cars and electronic equipment, and that in all these cases radiation plays a role. So if you are sitting in front of your campfire, think about heat transport by radiation. Success with the exercises and watch the glass plate example.